This is a video about hypothesis testing when the parameter of interest is the population mean. So let's start out with some review, some reasoning of tests of significance or hypothesis tests. We want to know what would happen if we repeated a sample or an experiment many times. We want to know how likely would it be that we would see the results we saw if the claim of the test were actually true, the null hypothesis. We want to see if the data gives evidence against the claim or towards the claim. And so we perform these hypothesis tests to see where the evidence points us. The null hypothesis. The statement that we are testing is called the null hypothesis. And the test assesses the strength of evidence against the null hypothesis. Basically, it tells us how likely or unlikely the null hypothesis is to actually occur. When performing a hypothesis, we have to assume that the null hypothesis is true. And we build our model based on the null hypothesis being true, based on the mean actually being that mean that we call it in the null hypothesis, until or unless we have sufficient evidence against it. The alternative hypothesis, H sub A, is a statement that we're trying to find evidence for, and it should express the hopes or suspicions that we bring to the data. Sometimes it's hopes, like a new drug is being developed and we want it to lower cholesterol levels in people. So we start with, and we want it to lower them, say, below 200. Well, we would start with a null hypothesis that says the cholesterol level of these patients taking this drug is 200. And the alternative hypothesis is that it's less than. And we're hoping that we can find evidence for the alternative hypothesis because we hope that it's true. Sometimes we're trying to find evidence that somebody's cheating on something, say they're putting more defective pieces into a shipment than they should be. And so that would be a suspicion that we're bringing to the data. And either way, we're expressing those in the alternative hypothesis. And we have to state those before we look at the data because we are cheating when we look at the data and frame the alternative hypothesis to fit what the data seems to already show. Hypotheses for means are the same as for population proportions. We have the null hypothesis saying that the mean equals mu sub 0, and alternatives, the one-sided ones where it's either greater than mu sub 0 or less than mu sub 0, and the two-sided alternative where we say don't care if it's greater than or less than, just want to see if it's different. And p-value is the same too. We assume that the null hypothesis is true. We create or calculate a test statistic, and then we look to see what's the probability that we would have a value that extreme or more extreme. In other words, put that on our curve and then see what is the probability in that tail. And we call that probability the p-value. The smaller the p-value, in other words, the less the probability that we could get that extreme, the stronger the evidence against the null hypothesis. And just like population proportions, when its mu is greater than mu sub 0, it gives us the probability of getting a value as large or larger. When it's mu less than mu sub 0, it's the probability of getting a value as small or smaller. And when it's not equal to, it's just twice the probability that it getting of the value as larger or larger than the absolute value. Because remember, we have to get both tails into it. Now this is something we didn't discuss in the video about population proportions, but it was in your reading and in the examples. A p-value, so sometimes we'll just say, you know, what's the likelihood of this happening? Then we can look at a really small p-value and say it's not very likely. I'm gonna say the null probably isn't true, and my favor is for the alternative hypothesis. But sometimes we're gonna have a significance level, and we call that alpha. And if the p-value is less than alpha, then we say, well, that's what we call statistically significant. And what that means is the p-value, the probability of this happening, if the null hypothesis were true, is smaller than what I'm giving as a tolerance level. It's too unlikely for me. So I'm going to reject the null. Now we can choose different alphas. A very common one is 0.05, but another common one is 0.01. Sometimes 0.1 we can tolerate that. So it really depends on what we're doing. If it's life and death or if it's not, that could make a big difference. So the smaller the alpha level, the stronger evidence against the null hypothesis we demand before we will reject the null hypothesis. Okay, there are some conditions if we're going to do inference about a mean. Data needs to be from a simple random sample. The population should have a normal distribution with a mean of mu and a standard deviation of sigma. Sorry. But both mu and sigma are usually unknown. And when we talked about using z procedures for things, we always knew sigma. So we need to talk about what to do about that. We can use inference to talk about mu, but we cannot use the z procedures because we have an unknown sigma. So let's look at our solution to that. We're going to estimate the standard deviation for the population with the standard deviation for the sample. And when the standard deviation of the statistic is estimated from the data like that, we're going to call it standard error instead of standard deviation. So instead of having sigma over square root of n, we're going to have s over square root of n. So that's one thing that we need to change to accommodate this. So now we have a one sample t statistic instead of z. And all we're doing is calling it t instead of z and substituting s for sigma. But when we do that, we're no longer quite on a normal distribution for that distribution of sample means. We're now on what we call a t-distribution with n-1 degrees of freedom. Looks really similar. Similar in shape, it's symmetric, centered at 0, bell-shaped. But the spread of a t-distribution is a little bit greater. In other words, it's slightly fatter. And how much slightly fatter depends on the degrees of freedom. Because as the degrees of freedom increase, and degrees of freedom are n-1, so that means as your sample size increases, the curve approaches n01. Because S estimates sigma more accurately as the sample size increases. So it just becomes so much closer. So here are what the t-distributions look like. You see, this is t-distribution with 2 degrees of freedom. It looks like a normal curve, but look how much higher we are off of this line. This one in here, the less dashed one, is 9 degrees of freedom. And right here is the standard normal. Same shape. they look very similar, but they're just slightly fatter and up from this asymptotic line. Now let's talk about what we call robustness of these T procedures now that we've introduced this new curve. They're exactly correct when the distribution of the population is exactly 100% normal, which almost never happens. Because no real data are exactly 100% normal. So the usefulness depends on how strongly they're affected by the lack of normality. So we call these T procedures robust if the confidence level or the p-value doesn't change when the conditions for use of the procedure are violated. And it's when you have something that is incredibly normal or a very large sample size that happens. So here are the criteria that you're not supposed to violate. Data from a simple random sample. That is the most important thing. Simple random sample. More important than the assumption that it's normal. If you have a sample size that's less than 15, you can use the T procedures if data appear close to normal. So if you have the actual data, you will want to do either you want the stem and leaf to see what it looks like, or a histogram to see what it looks like, or something like that. The data is really skewed if there are outliers present at that sample size. Do not do it. Won't have good results. I mean, reliable results. The sample size is at least 15. They can be used except with outliers or strong skewness in the data. And large samples, roughly n greater than or equal to 40. Some people tell you n greater than or equal to 30. But when you get that big, you can actually use it for even clearly skewed distributions. So, can we use T procedures here? You want to pause it and think about it, that's fine. We cannot use T because we have a population here, not a simple random sample. Gotta think about that. Can we use T here? Well, here we can't because the data is strongly skewed to the left. So we can't trust those procedures for n equals 20. And we're 40, we could totally do it because we have a high enough sample size. Here, can we use T? Okay, so the data is skewed right, but there are no outliers. So we can use T procedures since n is greater than or equal to 40. I don't know what we want to do with this with the word length in Shakespeare's plays, but there you go. And can we use T here? We can because the distribution is close to normal. So really for any sample size we do out of here, we could trust it.